a couple of things. So we got to the point where we said we start with Bayes' rule for posterior probabilities. And the Bayes rule captures the prior knowledge we have about that problem domain and anything we have derived from experimental data by fitting a probability density for each of the classes, right? That's what it combines. So because it has absorbed everything about the prior and from the data, then that's a good thing from which we can make a decision. Yeah. And we just said if the posterior probability is bigger than, for this class is bigger than the other, we are going to call this class. It naturally extends to multi-class problems. So if you have 10 classes, then you say which of them is largest, and you can make a decision. More realistic would be two important points. One is that you may be in situations where there is a loss function specified, that the cost of misclassifying class 1 as class 2 may differ from misclassifying C1 class 2 as class 1. So then you have to take that into consideration when you use the posterior probability to classify. Yes. The second point is that you may not always classify just based on comparing. You might have a margin, and you might say that unless the posterior probability hits in the two-class problem more than 0.65, I'm not going to call class 1. Yeah, anything between 0.45 and 0.65, I'm going to reject as something on which I will not call a decision. Okay? So those are things that you can build on top of that basic. And then we said, if we make very restrictive, simplifying assumptions, under those assumptions, very simple classifiers pop out. And those simple classifiers pop out means two things. You can look at it in two ways. One is if there are assumptions that are valid, then you can implement this simple classifier. You can work backwards and say, if you were to decide to use a simple classifier because you don't have enough compute or someone conned you into buying a simple linear classifier, say, then under what conditions is this the best one? And you can test to see if those conditions are met. There are formal tests by which you can test for Gaussianity in data, you can test for covariances, all sorts of things come on top of it. But that idea should be very clear, that there is a simple, there is a framework, there are simplifying assumptions, out pops something. Yeah. In this one, so then we said if linear classifier is the thing to do, then we can go and build an algorithm that would iteratively pull out, train up a linear classifier, and that's what this lab sheet is about. Okay, so I would invite you to go and do these, not right now, but sometime at your leisure. And the algorithm just looks like this. So the algorithm says that there is inputs, that's the data. Each of the inputs is in D dimensions. And the targets that I have specified are -1 and +1. So -1 for those who failed the exam, +1 for those who passed the exam. So it's a two-class problem. So what would I do? I would first initialize the weights to some random value. And then I would just start running through the data at random. So I would generate a data, call one of the data at random. And then I would ask the question if for that particular data, if this is met. Yeah, what is this? This is going to be a linear function weighted by the ±1. Because I'm demanding that on the classes that are, on the students who are passing, my classifier should output a positive dot product. Yeah. And on the ones who are failing, it should output a negative dot product. So if I have the positive and negative captured in the target value here, then target multiplied by this should always be negative for the ones that I'm misclassifying. Okay, on the ones that I get wrong. And the perceptron algorithm is a very specific algorithm, which says that if that computed thing is negative, then you go and update. And that update simply is your new guess is going to be the previous guess plus some small learning constant times the data and the sign switched accordingly. Yeah. So that was one of the, historically this is very important. So there's a nice Wikipedia entry you can read about perceptron and its history and so on. Initially, there was a lot of hype around, hey, this one is behaving like a neuron, and so we can have some fun around it. And there is also nice work on actually building hardware with valves and stuff that you guys would never have seen. Yeah, I have. So the people actually built these circuits into which this, and the Wikipedia entry is a good one to read about it. So I'll not go into that. But then quickly it was realized that such a linear classifier has its limits, yeah, and that those limits were recognized a lot through this exclusive OR problem, which is not particularly exciting, but if you have 1, 0 and 0, 1 belong to one class, 0, 0 and 1, 1 belong to another class, then a linear classifier will not separate them. Yeah, and there was lots of discussions around that. This thing cannot be very smart like the brain because it can't do this exclusive OR problem. So we are now talking 50s, early 60s. Then it was recognized that a combination of perceptrons put together in multiple layers might be a way forward, but people did not have a training algorithm for it. Yeah? And we will see such a learning algorithm a little bit later. Okay? When you build a multi-layer perceptron, how do you train this and so on? This update rule that you see here, which you can immediately implement and have a look at, is actually a derivation of, is a result of applying gradient descent. So when you want to minimize something, and we'll see that with linear regression in a minute, you have an objective function, which is like an error as a function of your unknowns. Yeah. So how do you find the value at which this error function is minimum? Yes, that is a fundamental question for all of us. How do you optimize this? Yeah. The simplest way that you learn from childhood is that if you have this function and an unknown, you differentiate the function with respect to the unknown, equate it to 0, and solve. Yeah. Why would that give you the minimum or the maximum? Because differentiation derivative gives you slope. Yeah. When the slope is 0, then that's a point where, yeah. And you know whether that's a minimum or a maximum. How do you do that? So again, from childhood, you take the second derivative. Second derivative carries information about curvature. That curvature tells you it's the maximum or minimum, right? So that's about the only tool we actually have when we go from simple things like this to more sophisticated networks that we can build. Okay, this gradient descent that's the tool. That's the only tool we have. But on top of that, we have lots and lots of tricks to make it actually work. Okay? And we'll review some of them as we go along. One more thing, if you go into this one, a point that needs to be made is it's a sequential algorithm looking at things one by one. And if you run through that, you will find that I'm also constantly partitioning the data that I have into a training set and a test set. Yeah, and that's another important point that everyone should know, that I would always estimate parameters or train my model or learn something from a set of data given to me, but I would quote performance of that model that I have trained on data that I have not shown the model while it was optimizing. Yeah, so I would quote performance on unseen data for which I would always partition the data into training and test set. This is a nice simple problem because this is for my meant for teaching. So as iterations grow, the perceptron is seeing data one by one, and its performance, overall performance on the entire data set is going up and up, and it has learned it completely, yeah, both in training and testing. And that is because this particular example is consisting of data of this type, and this data is perfectly separable by a linear classifier. Yeah, so you can always find a solution that would perfectly separate this. So, and the reason for setting up this exercise in the class is that then students can now play with, you can bring those things together, you can make them overlap, and then you can see what happens, and so on. Okay, and there are a couple of little tricks in there, so I would encourage you to go through that. Okay, so that's perceptron. I think I have said this. Okay, so what we'll now do is we'll go and look at linear regression. One of these is linear regression. I think it's this one. Okay, so we looked at classification, and we'll now go and look at regression. So classification is where your targets given to you are labels. It's like pass or fail, passing class or failing class. Regression problems are where your target variable is a continuous value variable, like tomorrow's stock price or tomorrow's temperature, and so on. Okay. So data is always of this form. Xn goes input. The target is Fn here, because when I taught this, I had F as my target. So my apologies, it's not T anymore or Y anymore. Yeah. So, and this is all deliberate, right? So this is to get you guys to think past notation, yeah, and think about the underlying concepts, not because I'm lazy to change the notation. Okay, so the input data is in some p dimensions, and there is real value target. I mean, a lot of what we will learn will also work for targets that are not scalars, targets that are vectors, but scalars are quite easy to write the algebra for. Okay, so in linear regression, we would have a model that's linear. Yeah, so the model says that your target that you want to, your response is a linear function of the inputs plus some offset. Yeah. Often in this algebra, it's easier, it's a bit cumbersome to have a vector dot product and a little term that's a scalar that's being carried through. So what we could do is a little trick that we often do, which is to say, extend the dimensions by 1, yeah, and append a 1 to this x and call it y, yeah, and append this w0 to w and call it an a. Yeah. What have we done now? Now our notation doesn't have to carry through a dot product and a scalar all the time. This scalar has been absorbed into that. And our model now is going to be data given as y as input and f as target. And the model is going to be y transpose a. Yeah, instead of w transpose x plus w0, all we have done is we have moved from p dimensions in which you set up the problem, in which I needed a slope and an offset. I have absorbed the offset and call it something happening in p plus 1 dimensions. Okay. The copies of these slides are in your team space, so you don't have to write as fast as I speak. Yeah, but because I have to cover a lot of material, I've switched back to here instead of writing on this one, which I generally prefer. But anyway, yeah. Okay, so that's what we have. Okay, so you gave me some data. My job is to fit a linear function. I have massaged this offset term in and set up my function like this. What would I now need to do? I would now need to write an error between the targets and what my function is going to output. Yeah, and then minimize that error with respect to the w's and the w naught, or in this case, with respect to the a's. Yeah. So let's write that in longhand algebra and then write it in matrix forms. If you wrote it in longhand algebra, the error is going to be what my model gives me on data n, take away the target of data n, square it, add it up over all the data. That's a squared error. Yeah. Normally, we would also write mean squared error by sticking a 1 over n in front of it. Some people would put a half in front of it so that when you differentiate this, the 2 cancels the half. And these are just fashions. They don't change life much. Okay. So that's the error. And that error, if you write it out in longhand, would look like this. Because all I have done is this dot product that's sitting here, I have written as an expanded version. So you know dot product is multiply each of the corresponding elements and add them up. Okay. What would we do to minimize this E? We need to differentiate this. We need to differentiate this with respect to each of the A's. Yeah, there are p plus 1 unknown coefficients A's. I'm going to have to differentiate this with respect to A's. And the way I would do partial derivatives is to pretend that all the A's but one of them is constant and differentiate with respect to that. Yeah, and when you differentiate with respect to that, how would you differentiate this with respect to AI, say, then the 2 comes down, the whole thing stays, and then you go inside this and differentiate, then only the AI term would remain, which gives me that expression. Okay, let's see if that is clear to everyone. I'm going to claim that what I have written here is the derivative of E with respect to one of the unknowns AI. Yeah, and how did I get there? I got this 2 coming down here, the 2 is here. And this is a sum of terms over all the data. So the derivative is also going to be a sum of terms over all the data. Yeah, if you have several functions added together, Then you differentiate, is the derivative of this plus derivative of this, derivative of this, and so on. With me? Yeah. And what do each of these terms give me? The 2 has come here. Then when I go and differentiate inside, I have to look at this part. When I look at this part, when I look at this part here, so J goes from 1 to P plus 1. It goes from A1, A2, A3 up to A10, say. When I differentiate it with respect to A2, then only the second term in that expansion will make a contribution. Everything else would be 0. Yeah, and that's how I end up with the YNI, because YNI is the term that multiplies the AI in that expansion. Okay. It will be very easy. If you are not familiar with this, just write it out for 3 terms. If you write it out for 3 terms, A1, A2, A3, then it pops out very easily, and it's a good thing to actually do. But what this would give me is P plus 1 derivatives obtained as derivatives with respect to each of the AIs, A1, A2, A3, up to AP plus 1. Yeah. And on the right-hand side here, on these expansions, I have all the A1, A2, up to AP plus 1. Yeah. So when I equate this to 0, you should understand there are P plus 1 equations and P plus 1 unknowns. Yeah. And that's what's important here. Okay. In almost any such linear regression problems, you would differentiate with respect to the unknowns, equate to 0. And if you have 10 unknowns, you will have 10 equations. Yeah, 10 simultaneous equations, 10 unknowns, you can just solve them. Okay. I think I've just written this in matrix form. Yeah, it's nice to write things in matrix form instead of writing them as lousy, longhand algebraic equations. So in matrix form, you can see that all the unknowns are sitting here. Yeah, and this is of the form like AX equals B. Yeah, and in here are lots of terms, and these terms will have this structure: sum over all the data, YNI, YNJ. And on this side would be terms as this would be a vector of the same length as P plus 1, and each of these terms would still be sum over all the data, target times the corresponding element. Okay, that's all lousy. So you can do this quite neatly once you will go and read the matrix cookbook and Gilbert Strang's stuff that I described yesterday. Yeah, then you will do this much neater in very small number of lines of algebra. So let me define a matrix Y into which I'm going to stack all the data. So remember, Yn is all the input data given to me. I'm going to take each of this data, make it horizontal, flip it, yeah, and stack it into a big matrix. Yeah, and that matrix is going to be number of data times the dimensionality I'm working with. Let me take a vector F into which I stick all the targets. Yeah, F1, F2 up to Fn, all the targets are going to sit in this vector. I can immediately write this error as this one. Yeah, can you understand this? So F consists of all the targets. Y consists of a matrix whose rows are the data. If you multiply by that matrix this unknown vector A, yeah, then this will give me an n times 1 vector of the same dimensions as F. With me on that? So Y is going to be n by P plus 1. This is going to be P plus 1 by 1. Yeah, so that will multiply. And the P plus 1 goes away. So this product is going to be n by 1. And each of those terms is what A predicts as the target is going to be. And this is actual target. Subtract this from that, and the norm squared of that is the squared sum. Okay, so that's much less to write, saves pen, chalk, ink, whatever, yeah, than working in with longhand algebra. And from this also we can immediately manipulate, and that's a skill worthy of development. And the matrix cookbook is the place to go. Yeah. Oh, and there's a homework in between. If you had done my course, then you would have to actually do this under pain of death. But okay, what you can now do is to compute gradients. So that's the error. The gradient is partial derivative with respect to each of the components of A of that error. Yeah. And if you differentiate that, then the 2 comes over here, and you have y transpose times this ya minus f. Yeah, and that writing that is not obvious. You have not studied this in primary school, but the matrix cookbook tells you how to do this. Yeah. And then what do? I've computed the gradient, and I go and equate that to 0. So y transpose ya sits here. Y transpose f goes to the other side of the equation. And I can compute the inverse of y transpose ya, multiply y transpose f. I have got an answer for A. So what have I done to get here? You gave me data, x's, and you gave me targets, f's. Yeah, and you wanted to build a linear model. That was the job set to me. So I made life a little bit easy by saying, okay, I don't want the slope and the offset to be separate because algebra becomes lousy. So I attached the offset to the unknowns and called it A. To your data, I appended to each one a 1, yeah, and called my data in p+1 dimensions. And I took all the data that you gave me, flipped them horizontally, and stuck them into this big matrix Y. Yeah, and once I have this big matrix Y, I also put all the targets that you gave me into a vector F. And once I have the vector F and the matrix Y, all I need to do is to write this line, and I have an answer immediately. Yeah, so that'll be just one line of code anyway. Okay, and all this has done is to give me the best fitting slope and intercept inside A that goes through your data and try to predict the target. Be with me on that. Okay, so now comes a couple. Okay, so again, another piece of homework under pain of death my students have to do is to write it out, all of this for just 3 data points in 2 dimensions, I think. Yeah, 3 data points in 2 dimensions, just to make sure that the longhand algebra, which was very obvious, matches this vector notation that's sitting here. Yeah. There are, okay, so a couple of things that could be said here. One is that I said I can compute the gradient, and then I can equate it to 0 and compute the solution, yeah, in one step. Yeah. But when I have the gradient, I can also do some other funny thing, which is to say, I want to make a guess of A, yeah, and use the gradient to little by little, improve my guess. Yeah, and that's what I have here. What I would do is I have the gradient, and I would write what's known as a steepest descent algorithm. And what this steepest descent algorithm is going to tell me is that, sorry, that should be a bold A. So I have some initial guess of the unknowns. And at iteration k, I would use the direction of the gradient to take a small step. Yeah. So imagine a ball like this, which is your error function. And wherever you are in some place, if you compute the gradient, the slope tells you in which direction to go to find the lowest point. Yeah. So I can start from some random guess, and little by little, multiplying by a small constant, yeah, take little steps and get towards the bottom in an iterative update like this. Yeah, this is a very powerful thing. This is what drives quite a lot of the literature at the moment. This is just about the only tool we have at the moment. Okay, so yeah.
What if A gets stuck in the local minimum?
So okay, so that's a good question. The question is, what if A gets stuck in a local minima? In a local minimum. In this problem that we are looking at, which is linear regression, yeah, the error function that we are dealing with is quadratic. Yeah, that's an important point. So we have y times a minus f. The largest power to which the unknown is raised is 2. Yeah, and that's easier if you look at the longhand form. So look at this longhand form in the second line here. Yeah, this is the error. The error is coming as a result of the dot product between the unknowns and the data, take away the target, squared. This error as a function of the unknowns A is quadratic, because the largest power to its A is to which A is raised is 2. You cannot have, you will have a constant, you will have a term in A, you will have a term in A squared, but you're never going to have A to the power 23. Yeah. So as long as it's quadratic, you will have only one local minimum, one minimum. Yeah, so there's no difference between local and global. As soon as you have nonlinearities in them, such as we will look in a minute with neural nets and so on, then the error function is no longer quadratic. And the place you would get to by gradient descent is the local minimum closest to your starting point. Yeah, so come back to this algorithm. This algorithm will get you to the local minimum closest to the starting point if the error surface has multiple minima. Okay. And then we have tricks by which we can jump out of such local minima. Yeah. You could also see immediately here that if this choice of this learning rate or this constant is important. So suppose you imagine a basin or a valley like this, you start from somewhere, you decide based on the gradient, the direction is that way to go. If you took a very large step, you can overshoot the minimum. Yeah. If you took a very small step, then it'll take very long before you reach that minimum. Yeah. So that has to be balanced out. And there are various tricks by which we can even have adaptive learning rates. Yeah. So that depending on the local gradient, we might take large steps or small steps. Okay, so that's gradient descent. And so obviously, that's a good point to say this. So eta is a learning rate. If you took it very large, then that's not very nice. You can overshoot. If you took it very small, then you will take a long time to reach the minimum. At that point, you can ask, then where is additional information as to how fast I should go? That additional information is in the curvature. Yeah, so if you're very flat, there's a difference between being very flat, then you have to take large steps. Or if you're in a very steep valley, you should take very small steps. Yeah, and whether the difference between whether it's flat or whether it's a sharp valley is the curvature information. Yeah, and curvature comes from second derivative. Yeah, second derivative tells you about curvature. And so the Newton's method of optimization in these is to compute the second derivative, which is called the Hessian, and update your AK by Hessian inverse times the gradient. Yeah, but this one in optimization literature doesn't always help us for a couple of reasons. One is that we often work with large models with many, many parameters. So dimensionality P is very high. So if P is very high, dimensionality is very high, then this matrix is P squared. The second derivative is the square of the number of unknowns. Yeah. So such a matrix needs a lot of space to store. And more importantly, such a matrix will not always invert. There's no reason to think this will invert because you're computing this from small amounts of data, so it may not invert. So even though this second order method is very fast, it's the way to go because you can measure the curvature and then you know how far to go. It's not the most practical. And the way you would then deal with is there are many practical algorithms that fall between these two. Yeah, so there's the gradient descent with a single learning rate. There is second order methods that will invert the Hessian and multiply the gradient. But that is, then this is troublesome because we don't know how to choose this. This is difficult because it's matrix, it's a very large matrix that needs to be inverted. And matrix inversion, almost like I said about cursive dimensionality, that's a nasty thing to do because the complexity of matrix inversion is cubic in the size of the matrix. Yeah. So you don't want to sit there inverting matrices. That's not a good thing to do. Yeah? Small matrices you can invert, large ones are very complex. It'll take, if you double the size of the matrix, it's going to take 8 times to compute that. Okay, so that's not a good idea. So there are many practical algorithms that fall in between the two. We'll touch on some of them in a minute. Okay. Yeah, so rapid convergence with second order methods, but cost of computing inverting it can be high, and we'll see that later. The other is an important distinction between what we do as gradient descent and the topic of stochastic gradient descent. So gradient descent, as we saw, was to say, take the error, differentiate it, and then use the gradient to iteratively improve. Okay. Now, the error was a sum over many terms. Each one was a data term. Yeah. So when you compute the gradient, you will compute terms over each of those data and add them up. Yeah, that will be the full gradient. If you look at the gradient expression, it has a sum over all the data. But you don't need to do that. You could do the update based on every single data point, pretending that that is an estimate of the full gradient. Yeah. So what you will have is that the true gradient is a sum over all the terms, all the data terms, and you don't need to wait till all of them. That as soon as you see the end data, you compute the gradient on that one and use that to update. And if your data is randomized, then there's a stochastic gradient descent. And this has actually, you would do that for convenience, yeah, because I'm going to sum over all of them and then update anyway. And every time I see this, let me update. So if you think of a quadratic error function for linear regression in which you're doing gradient descent, if you compute the full gradient, you will have your error going down very smoothly. But if you were to use every data point's estimate as an approximation to the gradient and then keep trying to go down, your descent would be noisy. Yeah, the difference between smooth trajectory and a noisy trajectory. Because at every data, at the arrival of every data point, you compute this term and you're going to claim that that is an approximation to the true gradient. Yeah. So every data point is not going to give you the same indication of what the gradient is. So your descent would be noisy. Okay. However, that has some advantages too. So in modern literature, we almost always use stochastic gradient descent. Yeah. Or we do a subsample of the data on which we compute the gradient. Yeah, in a small batch and then compute and do descent. And these not only have computational advantages like or conveniences, but actually also tend to have performance reasons. And that goes back to your earlier comment about what happens if you get stuck in a local minima. Sometimes when you work with stochastic models or stochastic ways of doing things, you give yourself a chance to escape from local minima. Yeah, and that leads to better solutions than if you were to do the proper gradient descent. Okay, so now comes another important point, which is about regularization. So what we said so far is you have some data, you can compute a solution to fit a linear function. That's what we have seen. And you can do this in two ways. You can solve a system, as it's shown here in this slide, up here, or you can do gradient descent in two ways using the proper gradient. You can also use stochastic gradients. Okay. If you do this like this, numerical analysts have noticed this long ago. If you multiply these, invert, multiply the transpose, multiply the target, this is numerically very unstable. Yeah. So this expression, this side of F is known as a pseudo-inverse. So you know if you have a square matrix, you can talk about an inverse of a square matrix. Y is not square, it's number of data times dimensions, or dimensions plus 1. So it doesn't got an inverse as we conventionally talk about an inverse, but this one is a pseudo-inverse. Yeah, so Y transpose, Y inverse, Y transpose is known as a pseudo-inverse. Okay. This pseudo-inverse computed from real data is often not numerically stable. Yeah, it won't be numerically stable under conditions where this can be close to singular, and this can tend to be closely singular if the features are correlated. If the x's that you gave me are correlated, then these y's have columns that could be linear combinations of others, or some of the data may overlap. And those reasons would make this numerically unstable. Yeah, so if you have round-off errors when you actually implement them on real computers, those round-off errors can propagate as you keep trying to do this. Okay. So what would you do? You could go and plug in a regularizer. What would this regularizer do? Instead of Y transpose Y to invert, because inversion is where the problem is, I would add a small gamma times an I sitting there. A small diagonal matrix that is added on to that will get me out of this numerical problem. And this has been in the literature for quite some time. Okay. Where did we get that expression from? We got that expression from minimizing an error between Y times A and F. Yeah, we wrote out the error, differentiated it, equated it to 0, and got that expression. I can go and write a slightly different error, which is this one. And what is this error going to tell me? This is going to tell me, this is what we saw before, YA take away F. Yeah, and this is the error on the data. So the input data here, responses here, unknown parameters here. So this is my error on the data. I penalize the solution by the norm of the results that's going to come out. Yeah. So now this error has a data term and a term that constrains A from reaching very large values. And gamma sitting there is a parameter that I'm going to tune, and I'm going to call it a hyperparameter. Yeah. A is the parameter that you want answer for. And in the process of deriving it, I'm using a hyperparameter here to get rid of some problems. Yeah. And what's the effect of this? You can try and understand this by saying that, what if I set gamma to very, very small values like 0? If I set this to 0, then the optimizer is only going to care about the data. Yeah, and that's exactly the same as what we have seen before. Suppose I set gamma to a very large value, yeah, then it's in the interest of the optimizer to completely ignore the data and set A to 0. Yeah, you ask yourself, minimize this one, then an optimizer minimizing this one, should gamma be very, very high, would be interested in setting A to 0 to cancel that one and would forget about the data. Yeah, that's the other extreme case. So that would be, should immediately be intuitive that then the result of that would be the values in A would be restricted from taking very large values. Yeah, and that's the regularization idea. Yeah. The homework immediately is that you should be able to differentiate this one, like what we did with this term, equate it to 0 and get that as a solution. Yeah. So this solution that I introduced as a numerical analysis fudge to solve instability in computation actually comes from a quadratic regularizer placed on the error function. With me? Okay, I'm free to add other types of regularizers here. Yeah, this particular regularizer that I know is going to give me, restrict the values of A from reaching very large values. There's another one, which is quite cool, which is known as an L1 norm. And the L1 norm is to add the sum of the absolute values of each of the coefficients as this regularizing term. Okay, and that's known as the lasso. I've forgotten to write the term lasso here, but the fourth book that I said you should all study, yeah, by Trevor Hastie and Tip Shirani and so on, have really cool explanations of what this L1 norm does. And what it actually achieves is it will switch off several of the AJs depending on the weighting that you have here. Yeah. So just the same way, this quadratic regularizer compresses the values that these parameters can take. What this L1 norm regularizer would do is small values, it will push to 0. Yeah. So if it pushes small values to 0, then in the solution for A, only a small number of them would be non-zero. Yeah. So when a small number of the data are not, the parameters are non-zero, it's legitimate to call that a sparse solution. Yeah. So you started with A, which has P plus 1 unknowns. You derive a solution in amongst those P plus 1, half of them are going to be 0. Yeah. The other half not. Yeah. So what it means is you started asking for 10 parameters to fit the line, fit a surface. You end up with only 5 non-zeros. It will not be as good in fitting as using all 10 parameters. Yeah, that we should know on the training set, but we may hope to achieve other useful things out of it. Yeah, so, and like I said yesterday, we are good at collecting lots and lots of data. Yeah, but only some of the data may be useful to make an inference in any particular setting. We have accumulated lots of other data that's irrelevant. Yeah. So it's legitimate to call for a sparse solution if you suspect that some of the features you have measured are irrelevant, only some of them are. Even though if you throw all of them in, you might fit the data slightly better. Yeah. Even if those are not relevant, just on a finite training set that you have, that might contribute to lowering the error a little bit. Yeah. But to make a statement about the problem, to understand what's going on, you might think a sparse solution is better. You might also think if you have a sparse solution, then that's a good thing to, I don't know, implement on dedicated hardware that's running off a battery. Yeah, you might compromise on some of the accuracy, but a sparse solution may be implementable in a battery-powered device, maybe. So there are various reasons why you might look for this sort of thing. Yeah, but the cool thing here is that it's by choosing the regularizer or the term here, I can induce some desirable properties such as smoothness, such as sparsity. Okay. Okay, so now before I go to the perceptron again, what I want to do is to show you one of the other labs. Lab sheet 1. Oh, I don't know how to find this. Yes, okay. So if you go and look at lab sheet 3, in lab sheet 3, you are taken through just linear least squares regression. You can implement this one in just one line of code, and then you can call scikit-learn's linear regression fitter, yeah, and then compare the results whether your pseudo inverse and the scikit-learn solution are exactly the same. And then you can go and run regularizers on this, yeah, on a problem that I have chosen here. And what you will end up with is this is a good comparison that you can make. So in that regression problem, if you did a pseudo inverse solution, all these 9 parameters are contributing to that regression. Yeah, so this one is large here, this one is large here, and so on. If you regularize it with a quadratic penalty, yeah, then what you'll see is that the values that they reach are constrained. They cannot all reach large values. They're compressed. Yeah, and that's the best you can have if you penalize quadratic with a particular weight on the regularizer. Yeah, if you throw in an L1 regularizer, then what that's going to do is the 4th one, 5th one, and the 7th one have been pushed to 0. Yeah, and the fitting is going to be achieved by the 1st, 2nd, 3rd, 6th, and the 8th coefficients here. I can blow up gamma a little bit more and suppress even more of them. If I blow up that gamma to a larger value, then the 1st one will also go to 0. A little bit larger, then the 6th one might also go to 0. And the fitting would be achieved by the 2nd, 3rd, and the 8th only. Yeah. The error on the data, as you keep doing that, will get worse and worse. But you gain on sparsity. Yeah. But as a modeler analyzing data, where do you strike a balance? That's your responsibility. Yeah. And that will come based on an understanding of the problem. Okay. Yeah, and on that, there is, again, there's a very nice illustration in scikit-learn's lasso path. What this means is as I increase the amount of regularization that way, as I go towards the left, what are these coefficients? So when I'm here, my regularizer is here, almost all the coefficients are active. When I increase the level of regularizing, when I'm over here, for example, only 1, 2, 3, 4 of them are active. Yeah. So you can derive a solution in terms of a small number of coefficients. Yeah, not all the features. In some cases, you might get very lucky, and those terms that remain forming the regression may be interpretable as something relevant to the problem. This is not always the case. Yeah. And there has to be an iterative process between understanding what's going on in that problem domain and the features that pop out when you do this. Okay. I have removed the solubility prediction task that I give my class because I think that's something you're going to do hands-on. Okay. Okay, so now if I go back to linear regression. Any questions before I shift here? Yeah.
Is there a regularizer that penalizes sparsity?
That penalizes sparsity?
Yeah. So say you've got an auto program data space mostly full of zeros. Is there a way to penalize that?
So I'm not sure if I understand the question correctly. Is there a regularizer that penalizes sparsity? So what are we doing? So we can fit the data alone with all the parameters and all the features you have, right? That's a full solution. You give me 10 features about, I don't know, students. Yeah. Oh, maybe my class might be useful. So suppose you tell me that I want to predict the grades of students based on time they spent in the lab and time they spent in the library. Yeah. So so machine learning grade is so much time spent in the lab plus so much time spent in the library. Yeah. So that's a full model with 2 parameters and 2 features. It may well be that the bar is irrelevant. Yeah. Machine learning is best learned with beer. Yeah. This is true. Yeah. So if that happens, then a sparse model should switch off the time spent in the bar and will be predicting your machine learning grade purely based on the time you spend in the library. Yeah, so that's going to be a sparse model. Yeah. So there isn't a question of penalizing against that. That is exactly what I want to achieve by penalizing the use of parameters. Yeah, in order to derive a sparse model. Yeah. If I don't impose such penalties, I will be using both the measured features, time in the lab, in the bar, time in the library. Yeah, makes sense? Yeah.
So I think I can interpret that question separately. We mean that you don't plus alpha, but minus, like the minus is realizing. So we mean that you encourage every variable to contribute to the prediction. So what if you have minus instead of plus alpha?
Oops, what is this doing here? Okay, so the comment is, what if your regularizing term is negative? The weight of the regularizer is negative.
The parameter to not be 0, so like it implies to contribute to the prediction. So it may be useful in situation as assumed when you have not many file, right? You don't have dimension of the data is small, so you encourage the prediction to
I think to some extent, I don't know. So to those on the call, the question is, we have a data error plus a penalty term weighted by a positive number. Yeah. What would it be if this number is not positive but negative? So to some extent, we are getting into guesswork territory there. I can't really see what that would actually do.
It's still quadratic, correct? So it's still
it will have something, yeah. So, but no, I can't guess this. So instead of guessing this, so I can set this as homework. When you do the regression, just switch it to negative and see what happens, and then tell me. Okay, a deal. Okay, it's difficult for me to think that would encourage something in terms of use of the variables, because all the variables are there, unless you selectively apply on variables. So something like group lasso, which is a technique that tells you not to use the L1 computed over the entire, all the features, but have them in groups. Yeah, so then there is technical reason for doing that, because sometimes groups of variables are closely related, you want to keep them all together. Yeah, but whether you want to have negative numbers there, that I need to think through. Okay. Okay, so why is this not moving? Okay, so that was linear regression we did. We can go from that linear regression to try to understand where that perceptron algorithm came from. Yeah, so that's something I want to say very quickly. How are we on time now? 10 minutes to lunch. Okay. So what did the perceptron do? The perceptron said that I have data and I want to randomly sample this data and do error correction if it makes a mistake. Yeah. So what would be a suitable error measure? Because now that we know, we can define an error measure, differentiate it, and solve by gradient descent. what would be a good error measure for the perceptron? Yeah. If we said the number of misclassified data is an error, yeah, that would be a piecewise constant function in that space. Is that something you can visualize? So imagine I take a particular value for this unknown, yeah, which is the weights of the perceptron. And there is some data on this side, some data on this side. Some are misclassified, some are correctly classified. Yeah. Then I will have a particular error. Say 10% of the data are misclassified. Now, if I move the boundary, move that parameters a tiny bit, yeah, the boundary is not going to cross over anything, and the number of errors I make would still be the same. I move the boundary a tiny bit more, the number of errors would still be the same. But when the boundary I move crosses one data point, then the number of errors I make would go up by 1. Okay? And you can visualize it, right? It's a continuous space, and you have a finite amount of data. I put a boundary here, and I will have 10 errors, say. So I move the boundary a tiny bit, it's still 10 errors. Another little bit, still 10 errors. But when I cross one of the data points, it will become 11. Yeah, then it will stay 11 for a while, then become 12. Yeah, so if I use the number of misclassified data as my cost function, as my error measure, then that's piecewise constant. It will be constant, step, constant, step, constant. That is a lousy function. Yeah, I can't differentiate this. If I differentiate this, it's either 0 or an indeterminate. Yeah, so this I don't like. So what you could do is to have a suitable error measure, which is the sum of the dot products taken over all the data that's misclassified. Because remember, the idea of the perceptron is to compute a dot product, yeah, and based on the dot product, if it's positive, that class, negative, this class. Yeah. So what I could then do is to set up a function like this one, which is the dot product over all the misclassified data, and that would give me a suitable cost function that I can minimize. Okay? And the algebra on this is a little bit tricky. And the way this is derived, and I would like you to go through this at your own pace, I'll give you the outline of how to do this. What we would do is to say, okay, so there is a positive class and there's a negative class. Yeah. And what I want is a dot product that's positive here and the dot product that is negative here. This is what I want. Yeah. In the derivation of this, what we do is a little bit of an algebraic trick, that is to demand, if I were to switch all the signs of the negative class, just multiply all the inputs by -1, then I'm asking for a solution that should make positive dot product on all the data. Yeah, is that something you can visualize? I'm given two classes. I want a solution that will produce positive dot products on this class and negative dot products on this class. Yeah, if I just switch the signs of all these guys, just multiply all these by -1, then I can say, okay, now I have a pool of data. Give me a solution, give me a vector that will make positive dot product on all of them. Yeah, that's the way they set up an error function. And once they set up that error function, you can compute its gradient because it's dot product, sum of dot products. And that gradient will be the data itself because it's just dot product. And the algorithm that would do that would be make a random guess and add to that the sum of all the data. You could also have a little constant here, yeah, that is misclassified. So we can think about linear regression, think about gradient descent, and also derive a gradient descent algorithm for a classification problem and not a regression problem. And you do that by setting up for yourself a suitable error function. And that is one of the major tricks in the machine learning literature now. Yeah? What you want to do is what is a good loss function to solve your problem. Yeah? And defining a loss function is almost like an art, and there are various ways of doing this depending on the problem. So that's what I want to hint at by saying this. Again, if the gradient algorithm is sum over all the data, you could do this, like I said before, a stochastic gradient algorithm. Yeah. So what would that stochastic gradient algorithm do? It will think that every time you see a data, that is the estimate of the gradient that's obtained by a sum of all of them. Okay. So that's the perceptron learning algorithm coming as a side effect, or as derived from the gradient descent. And that data is an item of data drawn at random, and it happened to be misclassified because the error is defined in terms of misclassified data, not over all the data. Okay. I'm going to skip the convergence proof of this. The convergence proof says that if you, and that's again another branch of machine learning that we are not going to, don't have time to touch on, that I can think of algorithms that iteratively try and improve a solution and give me something useful. Yeah. But will it always work? Or when will it work? How fast will it converge? And these are theoretical questions that people constantly ask. Okay. So even for this algorithm, perceptron learning algorithm, there were proofs that under some conditions, you will converge and terminate. When will that happen? If the data is actually linearly separable, then there is a solution. And if there is a solution, this perceptron learning algorithm will find it. Okay. You can go through that in the book and in the derivations I have here. And what it will lead to is to a result that says that, look at the just at the last two lines. Every correction I take, by taking a data, it's misclassified, I'm going to shift the boundary a little bit. Every correction I take will take me a little bit closer to a true solution if one exists. Yeah. So remember, I'm working with a data that's separable. If the data is separable, then there is a solution. Yeah, there is a boundary that will separate it. Yeah. And assuming that such a boundary exists, we want to ask the question, this particular algorithm that I have come up with, yeah, will it take me closer to an assumed solution than I was before? Yeah. And in the worst case, how rapidly would I get there? Yeah. So you can derive results like from some initialization, look at the last line, some initialization, we will find a solution in at most this many updates. Yeah. And that's the nature of the beast in many different convergence proofs in the literature. Okay. We won't go through that in detail step by step, but we can revisit this if you like, but let's just leave it there. Okay.